Okay, so we're gonna start. Even I see more people coming, but so welcome to day 3. You're almost done, and I'm almost done too. So today we're gonna be talking about tooling that you might want to use when you are working with Go, and we're gonna be working only on the most interesting tooling. There's some more advanced things that we're not gonna be covering, and there's a lot of tooling that is more basic, like Go vet, Go thump, Go lint, Go list, Go many things that I will not cover. But I will give you references so you can learn a little bit more about that. Because the idea is that we're going to be doing around 30 to 40 minutes of demonstrations of the tooling, and then we're going to have Q&A. Some of you send me questions, so I got all of the questions that you send me, and they're going to be answered with slides and references and stuff. But also, if you have any more questions, you'll have the time at the end to ask them. So, first thing, debugging. Someone asked me yesterday, actually you asked me yesterday, how do you debug Go? GDB. No, you don't use GDB. Why? Because GDB doesn't know about Go routines, and also the way function calls work in Go, the way stacks work are actually different to C. So GDB gets very confused. If you try it, it will probably work for a little bit, and then it will start giving you wrong things, which when you're debugging, if the debugger has bugs, that's an issue. So do not use GDB unless you want to have some awful fun. Delve is already it's version 1 point something, 1.1 or 1.2 already. So it's technically ready for production, and I've been using it for a while. It just works really well. It supports all 3 main platforms. On Windows, it is not as good because it's not as fast, but all on that works pretty well. And yeah, it's written in Go completely. It's open source, so you can find it on github.com/godelve/delve. Also, in order to install it, you do go get that, and that's it. That's installed. And it's a debugger that has a backend. We're going to be showing a little bit how to use the front end that comes with it, which is the GDB style front end, which is like the command line. But also, we're going to be using another front end, which is actually the integration with Visual Studio Code. There's integration for many other things. So let's do this. So today's gonna be some slides and some demo. So we have this program here. It's an HTTP server. And this HTTP server, this is all of the code. What this is doing is, so it's saying that we're gonna be handling all of the requests with the function handler. And handler, what it does is compiles this regular expression, checking that it's something alphanumeric with @golang.org at the end, checks whether it was able to find it. If it was not able to find it, it will print hello stranger. And if he was able to find something that says the path was whatever @golang.org, it will use that whatever as the name. So it would say hello, whatever. Okay? So let's see if that works. So go run main.go. Localhost 8080, they should say, hello stranger, great. And then if I say campoy@golang.org, which is my more official email, it says hello stranger. This is broken. It's not what it's supposed to do. It should print hello Campoy instead. So we could read the code and try to debug it. So try to understand what is wrong in here, but instead let's use the debugger. So the way you use the debugger here, it's delve debug. So when you do this, what's going to happen is we're going to compile the program with all of the different optimizations turned off and with as much information into the binary as possible. This is something that might happen probably. It will ask you for root access because it's going to be doing something that most computers will say, this is kind of dangerous. Are you sure you're going to allow this program to do this? Okay, so once you have this, it means that the binary has been compiled successfully with all of the ELF information that we could put in there, which is something that actually every Go version keeps on improving. So that's actually in the last 4 versions. The debuggers keep on getting better because the runtime provides more information.
The binary?
The name of the binary, it's DLV, delve.
No, but how does it know that it has to debug the main.go?
Oh, because it's compiling the whole package in that directory, which is package main, so it's a binary, so you know where to start. But now, when this is running, right? If I refresh this, it will not work, because this is actually not running. This is just, we loaded the binary, and we're ready to go, but nothing is happening yet. But if you do continue, now it is running. Okay, now we're actually running the program for real. You refresh, and it still doesn't work. But I mean, it still doesn't work the same way as before, right? The debugger didn't fix our issue, which is Domo, but at least the program is actually running. Cool. So what do we want to do next? Well, you can do Control-C, and that's going to pause it. But and it's going to say, okay, so where are we? You can print list. And probably it's going to be somewhere that doesn't make any sense. So we don't know where we are. We stopped in the middle of probably some runtime code, maybe written in assembly. So the debugger doesn't really know. But actually what you can do here is set breakpoints to say, actually, I want to stop at this given point, right? To do so, there's a couple options. One is you could do put a breakpoint at main.go line 30. That's something you could do, so it's going to stop here. The other option is main.go handler. So that is package main function handler. So you can do b main.handler. All right, now we set a breakpoint at the beginning of that function. Okay, so you need to give the name of the package and the function. And then continue, or C, shorter. Now when you refresh this, now this is waiting there. So we're here, you will see that the breakpoint actually worked, so now we are inside of there. So you can go next, or N, and then you can print things. So print the regular expression. Regular expressions are complicated and pretty opaque. So yeah, it worked. We were able to compile a regular expression, and there's some stuff in between. Not very useful. But let's continue. So let's see what we have in match. Match, it's saying that it's an empty slice. It's a slice that has length 0, capacity 0, and the backing array is nil. There's nothing in there, right? And that means that the defined string sub match did not work. It means that it was not able to find what you're asking to find. So that's interesting, right? Because it's saying that this regular expression doesn't match this field. So let's print that field. And that field says /campoy@golang.org, right? So can you see the mistake here? Yeah, the /, right? Like the problem is, oh, you're saying that there's that /, but you're ignoring it in the regular expression. The regular expression should have a / here, or we should drop the /, in the path. So let's do that. So this probably the easiest way to do it is simply say just ignore the first character and then continue. It's a slice, so you can do these kind of things. Okay, so let's try it again. Delf debug, continue, refresh. It doesn't work. Okay, so now we're going to use something different. We're going to be using, instead of using the debugger here, we're going to be using the debugger that is integrated into Visual Studio Code. So how do you do that? To set breakpoints, you click. And then to run, you click on the debugger, because that's a bug that is not there, debug, yeah. Start debugging. And so here it should say something eventually, or sometimes it doesn't say anything because there's nothing being logged. But as soon as you say that, you see that API server listening, that is the backend of the debugger listening to that, right? So now the Visual Studio Code integration, it's going to communicate with that. You can also develop something to communicate with that if you want to build your own debugger front end. Okay, so let's refresh this. And now directly, you see, it just goes directly back to the editor. And you can do, let me make it a little bit smaller. Here, this is kind of cool. There's an option which allows you to show the inline results. So you can see the match as soon as you run it, you have it on the right side. So now it's saying that it's match, it's length 2, capacity 2. And then the next thing we do is check whether the length is 1. Why? Because that's a bug. Match contains all of the whole string that was matched, and then the subgroup that we're interested in, right? So that is why this is not actually working. This is a subgroup. This is the whole thing. So you actually don't get one result, you get 2. And you are interested in getting the second one, the one that says Campoy. So this should be 2. Also, If this was true, this would be a mistake. So yeah. So let's save, refresh here. We did, oh, okay, so this is, so let's go step by step and see whether, now it goes inside and it will print match of 1, which means that now message is hello Campoy, and if we continue, it will go back again. Do you know why it's doing twice? So let's see, what is the request? What is the path? The path is, wait, the URL is here, net, path. Oh, because the one before, probably because I clicked twice. Something that happens pretty often is that it will also ask for the fabico.ico, which that messes you up pretty often, at least it happens with me. So just gonna continue, and there you go, so now it's working. So with this, with the debugger, you can do a lot of different things. There's a lot of information that you can get, not necessarily from this one, but from Delph directly. You can list all the Go routines that are running. You can list a bunch of different things that are interesting. In general, what you're going to be using for the integration with Visual Studio Code works enough. The integrations with other IDEs are pretty good. The integration with Vim is non-existent. So if you're trying to use Vim, it's going to be pretty hard, so you're going to have to use Delph directly. Cool, so that is the debugger, Delph. Any questions about it? Okay, so let's continue. Okay, so, oh, that was the debugging live demo. The code, by the way, I will share these slides, and this is a link to the code that I just debugged, if you're interested in seeing it. Okay, so debugging is great, but that's actually not how you write code. Normally, the way you write code is you write tests. So debugging is a tool that is great to figure out what is the test you should be writing, right? So how do you do test in Go? So it's something that is part of the standard library, testing. The testing package includes this already. And what you need to do is you need to define a function that starts with test, capital T, because it's something exported so the testing package can see it, and then test whatever. The name is up to you. It receives a pointer to a testing.t. Now that testing.t has all of these methods. It has more than those, but these are the important ones. T.error, errorf, fatal, fatalf. Error and errorf will mark the test as failure, but continue running. Fatal, fatalf will mark the test as failure and stop, and just go to the next test, okay? So let's do a quick demo. So I'm gonna add a test here. So this is something important. It's going to be something _test.go. And this is weird, but in Go, the name of the files determines whether you're going to be using them or not. So Go, if it finishes with _test.go, those files will only be considered when you do Go test. If you do Go build, those files will not be considered at all. The compiler will not see them, which means that all of this code will never finish in production. There's no way you can make this enter in production. You can also do main _Windows, main _Linux, main _Darwin for iOS. So all of these different ones, you can play with those. And then on top of that, there's other ways of deciding what to compile when, if you want to do more advanced things. Like, I want to compile this only when it's Linux on ARM32 and the version of Go is 1.7 or above. You can do all of these things. A little bit more complicated, and there's references at the end on how to do that. Okay, so the package is going to be either package main or package main test. You can choose. Main will be the same package, so you can test everything, white box, so you can see everything inside of the package. Main _test is a different package, which means that you need to import and use only the things that are exported. So it's black box testing. Here, since we're going to be testing something that is not exported, the handler, we're going to need to do it like this. Actually, to make it a little bit easier, actually, I'm going to do it just even easier than that. I'm going to be testing something completely different. Let's do func. Let's move this out of the way so it's easier to test. So, no, let's do it like this. So I'm going to do a sum. That's going to be a bunch of numbers. and it's going to return number. And this is going to be s equals 0 for value in, let's call this values, range values, s plus equals v, return s. All right, so this is our sum function. So let's try to test it. Test sum, we're going to do a testing.t, pointer to testing.t. And we're going to do something like, so sum of 1, 2, 3, that is the sum. And if sum is not 6, yes, t dot fatal f, expected sum to be 6, got something else. So this is a test, and this is basically how you're going to be writing most of your tests. So in order to run them, you do go test. And go test will tell you that we run some test and everything worked. Go test -v will give you details on exactly what we actually run. Let's say I don't know how to do sums. You will get something like this. It would say test sum failed and expected sum to be 6, but got 6. That's a pretty bad test. So okay, so now let's say that you want to have many tests, right? Like in general, you're not going to be testing only with one single value. So what you're going to be doing is you're going to be doing something like this, and you're going to say if you don't pass anything, that's going to be a 0, and that's going to need to be like this. And then if I pass 1 and minus 1, that should also be a 0, etc. So then I can do go test. And this still passes. The problem here is if one of them fails, and actually that should be a 0, that should be a 0. So if one of these fails, it is actually really hard to know which one failed, right? Because it's just going to say expected sum to be 0, got 0. So if this one fails or this one fails, you're going to get exactly the same error. And also you're repeating code, which is not a very nice thing to do. So what we do here is what we call table-driven testing. So what we're going to do is we're going to declare a slice of test cases. So normally I call it TT, TT for test table. And that's going to be a slice of structs. And in the structs, I'm going to have the numbers, which is going to be a slice of ints, and the sum, which is going to be an int. And then I'm going to define my cases. So I'm going to say, if I get 1, 2, 3, I expect it to be 6. If I get an empty one, I'm going to expect it to be 0. If I get minus 1 and 1, I'm going to want this to be 0 too. And then we're going to do a for loop, test case, range, TT. When you're doing a range over a slice, the first element you get is the index. The second one is the value. It's a copy of the value in the slice. Okay. So now I can move this here and do sum of tc.numbers to make that work with the fact that I'm passing a slice, but actually this expects a list of numbers, like a variadic argument. And if this is not equal to tc.sum, then I'm going to say tc.sum and that. And then I can get rid of this. Now, this is much easier to maintain, right? Because now if I want to add something else, I just add one more line. That's it. That's a new test case. So this is normally the way you want to test things. Now, if we do this, there's still a problem, which is we have not fixed the fact that when this fails, say this is minus 1, it's going to get expected sum to be minus 1, got 0. And if you had a couple of them that are all expected minus 1, this is not helping you. So there's a thing that people do, which is you add a name. So you say name is a string, and you say, for instance, 1, 2, 3, empty, and 1 and minus 1. And then you can say, I'm going to start with the name of the case and the error. Right? So now when it fails, it's going to tell you this is the test case that failed, and then this is why it fell. So let's try it again. This is passing, but if we say here minus 1, it's going to say main test, empty, expected sum to be -1 and got 0. Okay, so now you start getting a little bit more context. And this is something that we do so often that there's a way of doing this much better. So this is something that appeared in Go a little bit later after this became a normal pattern, a normal idiom in Go, which is what we call subtests. So you can actually have a subtest is something that you do t.run, and that is a function that receives a name and a test function. So you can do tc.name, and then a function that receives a testing.t, and that's the same thing. Now, when you're doing this, now the name is not necessary to use here, and the name is not necessary to be here. So now what we're doing is just saying to this function, hey, this is the name of the test, and this is the code of the test that you should be trying, right? So this is very similar to what we had before, but the testing package understands this, and the output is going to be a little bit different. So now when you do go test-v, you see it runs test sum, and it says also 1 to 3, empty, and 1 and -1. So now those are subtests, and the testing package is able to see those. And even better, you can now do things like go test dash run, I think it's dash run, and this is a regular expression. So if you do dot, everything's going to be run. Let's make it work, actually. So everything's going to run. All of the subtests. But you can also do dot/1. So now we're running 1 to 3 and 1 -1, but not empty, because that empty doesn't have the word 1 in it. So you can actually choose which ones you want to run. And this is pretty useful when you have things like, I'm going to be having a test case for this environment variable, test case for this size or whatever. You want to run only those. It's pretty useful to decide exactly which ones you want to run. And that's basically what there is to know about testing. There's some extra libraries for assertions and stuff like that, which I do not use ever, because the problem with assertions in Go is that due to the test system, very often you're gonna to the type system, you're gonna have things like you're comparing -1 as a float with -1 as an integer, and they're not the same value. And it will say false, and it will print expected -1 got -1, and you will be annoyed. So that's why I do not use assertion libraries, but you can use them if you want to. Just take that into account, that there might be issues related to the type system not being exactly what you expect. Cool. Any questions about testing? Okay, so the next thing is live demo. So benchmarks. It looks like a test, but it's not a test, because instead of starting with test, it starts with benchmark. And instead of receiving a testing.t, receives a testing.b. And the only difference that is relevant to you today between a testing.t and a testing.b is that testing.b has n. That n is the number of iterations that you should do. So it's the number of times you should be running that benchmark in this loop. Now, the way this works is that the benchmark is going to be run as many times as it takes. So it's going to start with, like, I'm going to run it once, and then twice, 4, and it's going to augment it exponentially until running it n times takes around 1 second. Okay? That is the goal. You can change that if you want to, but the idea is that it needs to get to a given point where it's going to be statistically significant. If your function takes more than 1 second to run, probably you want to modify that to say actually run it until like it's 1 minute or something like that. So it's enough iterations that it makes sense. So let's write one. So we're going to do exactly the same thing. So benchmark sum b testing.b for, let's try again, for I b.n. We're going to do sum. So we're going to say sum 1, 2, 3, 4, 5. Now, something important is you need to make sure that what you are passing, it's always the same, or at least all of the function calls are going to be taking the same time. So for instance, if you're testing Fibonacci and you're calling Fibonacci of 100 every single time, that's fine. But if you're calling Fibonacci of b.n, that's wrong. Because then what's going to happen is, depending on how many times you run it, it's going to be a different test. So the statistics will be on a bunch of different things that do not share the same distribution. So it will not make any sense. except that you will get a number. That number will be useless, but you will get a number. So you need to be careful making sure that the benchmarks that you're running actually make sense. So, okay, so let's run this. So you run it with go test-bench, and then you can do a regular expression as before. Dot includes everything, so run all the benchmarks. So now you're going to see that the benchmark here was run a lot of times, because this is a pretty small thing, and it took 3.46 nanoseconds, which is pretty fast, but I think it actually makes sense. Sometimes you might get, so when you're doing this, if it goes under 1 nanosecond, there's probably something wrong. In general, the Go compiler optimized the way your function call. That happens. So there's things like, actually, let's try it. You can do things like, I'm going to put that value in a variable that the Go runtime it cannot prove that might not be used later, so it actually cannot optimize it away. Let's see if it takes okay, so I think this made sense still, because that extra value is actually assigning that value into memory, so it makes sense. But yeah, if you go very, very low, there's a couple of examples. The Go compiler keeps on getting smarter and smarter, so the benchmarks keep on being harder to do. It will be able to do things like, if you pass 2 integers and the sum is doing inside like a sum, or even with float conversions or whatever, we use SSA, single static assignment, so the compiler is able to transform a whole function into saying, oh, this always returns this number, so I'm just going to give you this number. So then you're just assigning a constant to a variable. You're not calling any functions. So I will give you a link to things that you can see a little bit more in detail when you're running this. The most important thing is, if you're under 1 nanosecond, I mean, I don't know how fast the computers are at CERN, but if you're under 1 nanosecond for a benchmark, probably something went wrong and you're actually not benchmarking anything. Okay, so next is pprof. So pprof, the cool thing about pprof is that we're going to be able to see what is going on with a benchmark, what it's actually doing. So for pprof, I'm actually going to do, how could we do it? I want to do something a little bit more meaningful. No, I'm not going to do anything meaningful. I'm going to do something that works. So what you can do, if you have a benchmark and you want to get the pprof result of the benchmark, so how many of you have ever used pprof, actually? That's important. Pprof. Okay, so I'm going to explain what pprof is. So pprof is something really useful because basically it's a little program that runs next to your binary, and it's going to be asking your program, what are you up to? I think like 300 times a second, or 3,000, I do not remember, but very often. And every single time you ask your program, what are you up to? The result is going to be a full stack of all of the functions that you're executing, right? So basically the idea is that you're going to get an idea of how often you were running a specific function. You do not know in between those 2 questions whether you actually exit that function and went back again. You do not know, and pprof cannot answer that question. So everything you know is statistically how often you were executing a piece of code, okay? The good thing about that is if you get enough statistics, then you end up having an idea of what your program was in general doing. So to do it with Go, you simply do dash CPU profile equals cpu.pb.gz, pb.gz. You can call it whatever you want. I like to call it pb.gz because it's a gunzip procal buffer file. So that's why I call it like that, but you don't care because the tool will work no matter the name. So when I run this, now on top of doing what we were doing before, this is going to generate that cpu.pb.gz. And now I can do pprof, actually let me do it here, pprof cpu.pb.gz. And this kind of looks like the debugger, but it's very different because here the program already finished. There is actually a trace of what the program did. So you can do things like top. And this will tell you what your program was doing most of the time. Most of the time, this will be pretty useless because this will show you the function that you were calling the most often, which probably is something really deep somewhere under runtime. So it's not necessarily the thing you want to do. Top cumulative, that's going to be the interesting one because it's going to be basically the high-level functions It's going to count not only the time you were executing that function, but that function and the functions called by it, right? So that is more like the time that a function actually took. So here it's going to say that you spend 94.96% of the time running the benchmark, which is good. And then you're going to see different things that is going inside. This benchmark is very simple, so there's not much information in there. But basically, it's going to show you all of the things that we're up to. You can do web, and it's going to show you an idea of what your program is doing. So you have the benchmark that is run, and you have the actual benchmark. All of this is the benchmark framework. And then the function web server. Oh, that's the package. The function sum. That's what you were running 51% of the time. So actually, the function is so fast that most of the time you're actually running the benchmark and calling the function rather than running the function itself. But yeah, this can be pretty useful. What I'm going to use instead is pprof is great, and you can also use memory profiles and all that kind of profiles. But for benchmarks, it works well. The thing I really like is for web servers. So if you want to add a pprof features to your web server, it is very complicated. You do import net http pprof. That's it. Now, if you do this, this will not compile. And if you are using Go imports, it will disappear. Why? Because you're actually not using it. This is an old package from the standard library, and it uses side effects to register things. So to tell the Go compiler, I know what I'm doing, just leave it there. You can do import without a name, kind of like with variables, local variables. So now if I do this, I can do go run main.go, localhost 8080. This still working the same way as before. But now I can do debug pprof. There you go. And here now you can get all the information that pprof gets every single time you hit it. So this is pretty useful, but also pretty dangerous. So if you have, this should not be available from production to your customers because they will be able to take your server down quite easily. So now, once you have this, this gives you a snapshot of what happened right now, right? But the cool thing is that you can use pprof to start analyzing a running server. So say we have pprof http localhost 8080 debug pprof. I think it was this. Nope. Let's see. Pprof debug pprof profile. So close. Profile. And then you say how long you want it to run. 5 seconds. Seconds. I'm going to need to do copy paste more often. Seconds. Okay, so now we're running during 5 seconds. We're actually looking at what the server is doing. We're going to generate this, and now we can do web and get the result of what this was doing. It was not doing anything, which kind of makes sense because there's no traffic, right? So our web server is not doing anything. Okay. There's a cool tool that you can use called Go Work that I think is already installed. Yeah. So Go Work, you can do Go Work localhost 8080. Let's do campoy.org. HTTP. And this is going to be running during 10 seconds, just sending traffic there. So I'm going to run that. And no. OK, so we're going to send some traffic, start pprof, and now we're doing pprof while we're getting traffic. So now we should get something that is actually meaningful. Web. There you go. So now you can see all of the things that your server was up to. And you can see that most of the time, you are somehow reading from background read and regex compile. But this is something that I don't like. I think that pprof is a super useful source of information with one of the worst visualizations you could imagine. So hipsters use something different. You do the same thing, but you add HTTP a port. You send the traffic. You start the analysis. And now what this is going to do is actually, rather than just go into the compile, into the normal mode, console mode, it's going to show you the same information, but in this website. And this website shows you exactly the same thing, but also flame graphs. And flame graphs are much cooler. Because now with a flame graph, what you can see is what your program is actually doing all the time. So you can see that what you care about is probably somewhere in here, server handler, main handler. This is the code that you wrote, and this is what it's spending its time on. Right? So now you can see that actually most of the time you're spending your time compiling a regular expression, which is a pretty useless thing because you're compiling the same regular expression over and over and over. So how can you make this faster? And actually something interesting is that Go work will tell you the average request time, so 510 microseconds to finish every request. It's pretty fast. But so how can we improve this code? First you find it. Okay, so var done. Now the regular expression is compiled only once at the beginning of the program, and it's being reused, right? So let's run the server again. Let's run this. Let's run this, and see what happens. So after 5 seconds, you should be able to see that this became so small that you cannot even see it. I think it's this one. Yeah, serve HTTP. And that main handler now spends most of the time just printing to the output. And the time it went from 500 microseconds to 423 microseconds. Why? Because it's actually still really fast, and most of the time it's just reading and writing the request and the response. So most of the time it's there. You cannot increase that much, but still, you increased by a lot. You removed like at least 90% of the time in your code base. So that's pretty good. Okay. I have too many things going on right now. There you go. Okay, so yeah, flame graphs are a great way to show what things are doing. And so that is all of the demos that I'm going to be doing today. I think that this is like the basic thing. There's much more advanced things. pprof has a big issue, which is the fact that it only tells you the things that are going on when you ask it, right? So there's a different thing, which is the Runtime Tracer, that inverts the responsibility. And then what you can say is, hey, runtime, tell me everything you do. So then you're able to visualize things like when the garbage collection pause kicks in, when a new Go routine is created, when a Go routine blocks because of a channel, and you're able to visualize all of this data. Which means that, well, this pprof has a very small overhead. Like, I think it's around 5 to 10% only when you're actually hitting it, when you're doing the profiling, that you get a 5 to 10%, which is acceptable in production. When it's not on, it's completely zero. So every single server that you run, and I would say that every single binary that you have, if you want to know what it's up to, just add that line there. That's everything you need to do. So that way you can actually inspect what a map reduce is up to, right? So it's pretty useful. The Runtime Tracer, though, is not small overhead. It's big, big overhead. And it really depends on what the program is doing. So if it's something that is using a lot of concurrency with many Go routines and blocking very often on channels and mutexes, you can generate gigabytes of logs per second. So that's not good, because one, your program is going to crash pretty quick, and also it's going to go incredibly slow. So yeah, also, when you put this, also you're enabling people to go and do trace on your running program. So if you put this in production, you're actually allowing people to slow your program by like 100 times by just hitting an endpoint. So do not make that public. Let's make sure of that. Do not make that public. You make that public, your program will be down very soon. Okay, so all the things that you might want to learn, I actually made a video. It's like 40 minutes of different toolings that I use regularly. So the link will be there. The Go tooling workshop is a full day, going from editors and formatters and all the things that you use to manage your source code and the workspace, then going into how to build things, and then into more detail on all of the dynamic analysis that we have in Go. And yeah, there's a lot of things in there. And from the Runtime Tracer, I have a video too that explains how to use it by generating Mandelbrot fractals. It's a pretty cool example, and it shows you how you can actually improve the performance of a program by, I think it's something like 50 times, make it 50 times faster, but just using concurrency correctly. Right? So, and all of that is driven by the data coming from the tracer. So we have 20 more minutes, and the idea is that I wanted to do questions and answers. So there's a bunch of questions that I received via email. We're going to be answering those first, but also start thinking about what other questions you have, because there's going to be time for those at the end too. So someone asked, we're CERN, we do scientific computation, HTTP is cute and everything, but that's not what we do. Indeed. So how can I do it? GoNum, which has a beautiful logo. GoNum is a pretty cool tool. It's like NumPy, but for Go, and it's really fast. It is really fast because most of the time it uses conditional compilation to use the fastest assembly instructions when available. Right? So actually most of the time when you call sum, you're not going to be doing sum with a for loop in Go. Instead, you're going to be using some magical SIMD instruction that your machine could have, right? So in general, that's a very good idea to use, and it makes your programs much faster. I actually implemented a neural network in Go. The pure implementation was painfully slow, like really slow. But just by modifying one single function to call GoNum, it became 100 times faster. So it is worth checking GoNum. Goda is like pandas. So if you ever used pandas, which is a really cool thing, Goda is supposed to be like pandas. I have never used it. So good luck. I do not know if it's good or not. People say good things about it. So if you want to try something like that for data transformation and things like this, Goda is probably one you're going to use. And then github.com/TensorFlow Go. I do not know why they went with the name. It's ridiculous. But if you want to use TensorFlow from Go, you need to do import that. And there's bindings for Go. So it actually uses TensorFlow, the C code of TensorFlow in the back. But also, it doesn't support training. It's about to support it for 2 years. So I don't know if it will ever come. There's some experiments that say that they're going to be having them soon. But also, TensorFlow 2 is about to be released, which means that I do not believe that. Also, GoHep, so high energy physics. This is something that is developed by someone here at CERN, actually at CNRS, and he's the one that brought me here the first year, so last year. So yeah, Sébastien Binet, and I think that if you're really interested, talk to him, and I think it'd be an interesting thing to create some kind of community of people developing things in Go at CERN. That is the logo. And yeah, so if you want to get in touch with him also, that's him, Sébastien Binet. I'm assuming this is some cool CERN stuff. I don't know, but looks like it. Also, Go machine learning. So yeah, TensorFlow Go. That is pretty good. But there's also Gorgonia. Gorgonia is completely written in Go, and it uses GoNum below. So it's actually pretty fast. It works really well, but the documentation is incredibly poor. So if you want to use it and you want to contribute to an open source project, it's a very good idea to try it, suffer the pain once, and fix it so others will not. It is developed by Chui, which is a Chinese guy, and he's also the one maintaining GoNum. So they actually work very well together, both libraries. So it's worth having a look. And this one supports training. So if you're doing things like, from linear regression to basic neural networks, I've seen basic neural networks. I have not seen anything like convolutional neural networks on it, but I'm pretty sure that you could implement them if you want to. Another question was, I don't know why this logo is not here anymore. Just ignore it. Configuring Go programs. So if you have a Go program, do you pass flags, configuration files? How do you do this? And the answer is it's up to you. If you're doing things on Docker and Kubernetes, probably environment variables, that's what you want to do. But if you're doing something that is more like a CLI that people are going to be running, maybe you want to use flags. There's a very good package that supports both. envconfig by Kelsey Hightower. And I use it pretty often, and my company will also use it. We modified it a little bit. It also supports default values, and there's a bunch of different things. And it abstracts all the configuration away quite nicely. Another option is Viper. Viper is well known because it's what Cobra uses. And Cobra is the best way, in my opinion, to write CLI tools in Go. Writing CLI tools in Go is super nice because you get to generate a binary that then you can send around, right? MongoDB, for instance, they migrated all of their binaries, all of their tools for the clients from Python to Go because of this. Like 50% of their issues they were receiving were about, your tool doesn't work on my machine, and the answer was, we're using Python 2, not Python 3, you're missing this library, you're missing whatever, you're using the wrong version of whatever, right? So this solves all of those problems. So yeah, Cobra, I would definitely recommend it. If you're using Cobra, probably for configuration, you're going to use Viper directly because they're basically integrated. If you're not using Cobra and config, I find it simpler, which is good for a tool that does its job. And then for reading JSON, CSV, XML, all that stuff, the standard library has packages for that. They're not necessarily the fastest because they use reflection. And reflection in Go is not incredibly fast. That is more of a feature than anything. Actually, Go doesn't want people to use reflection that often. And people still use it all the time. So if you want to use something faster, there's actually godoc.org. You can find a bunch of different ones. There's some of them that will actually generate code. So if you say, I'm going to be decoding this struct from JSON, rather than using every single time you're going to decode it, reflection to figure out what's in there, you can generate the code that will that decoding. So then it will be much faster. That's probably the solution you want to go for things that are fast. Also, you can use other formats like gRPC and Procol buffers because that is actually really fast. Someone asked me, Go versus Python. I gave a talk about that. So there's actually 2 talks about that, which the other one I forgot. But there's Go for Pythonistas, so it basically explains the type system and concurrency of Go for people that know Python quite well. So that is one of the first talks I gave. There's another one called the Zen of Go, which is about how Go is better at the Zen of Python than Python. A talk that I gave in front of Guido van Rossum once, and that was fun. But he agreed. Basically, it's all about like the simplicity and all these different things, the principles of Python, and how they appear in Go. So from a philosophical point of view about the language, it's also really interesting. Why would I use Python rather than Go? Speed. It's one of the biggest things. For me, speed of programming, getting to a thing that actually works. In Python, the fact that there's no static types, it means that very often you're going to find errors a little bit later, which makes that the loop of feedback is a little bit longer, so it means developing is slower. Also, speed at runtime. The runtime of Go is much faster than the Python runtime, and especially speed when you're doing concurrency. Python has the global interpreter lock, which makes things painfully slow when you're using multiple threads. Go was designed already with that in mind, so it doesn't have that issue. So also, the global interpreter lock makes sense because it's an interpreted language, and Go is not. So that's why it doesn't have that issue. And also it has less magic. And when I say magic, I mean magic methods. So underscore, underscore, whatever. In Python, very often what the code does is not obvious, right? So that means that when you are, for instance, calling a function, maybe actually before you call that function, there's some other things that are going to happen in between. In Python, you can do amazing things, though, with that magic. So when I was working at Google, one of our test systems would replace the missing field. So if you try to get a field that was not defined on a type, it would just go find it somewhere else, which is cool, but also, oh my God, it's very complicated to understand what it's actually doing, right? You can do amazing things like when you get a field, actually go find it in a database. That is a thing that Ruby people love. It's cool when it works. It's very hard to debug. So depending what you're doing is good, depending what you're doing is bad. But also, this means that magic of Python means that TensorFlow, for instance, using TensorFlow with Python works really well. because the type system is very flexible. So when you're doing an addition of a matrix and a slice, a matrix and an array, it just works. It's just like cool, and it works. And once you understand how it works, it's actually really, really nice. And doing the same thing in Go will be much harder. So if I'm doing machine learning, probably I'm going to stay still with TensorFlow on Python for now. And that's it. So we have 10 more minutes for your questions. Yes?
Thank you for the talk.
Thank you.
What's the status of Go v2?
Ooh, Go v2. Yeah. So I do not think that Go v2 will ever happen.
Okay.
To be honest, I think that most of the things that we're talking about Go v2 are things that for now would break backwards compatibility, but we're going to be able to find a way not to break it. So for instance, there's things like generics. The proposal for generics, the current one, does not break backwards compatibility. It would something that you could add on top of the language. So hopefully it will never happen. The things that come with Go v2, the things that people are talking about, I think they're interesting. Contracts and generics is something that I really like. As a concept, the implementation and how it looks like, not much. So hopefully it will change. Like this is not even a proposal, it's just a design draft. So it's not even a design, it's just a draft of the design that might become a proposal. So we're really far from implementing it, but it's exciting. The other thing is about how to handle errors. I really don't like it. The way they're proposing how to handle errors with a thing called handle, I find it very ugly and not Go-like at all. So I don't think it will happen, but you never know. It really depends. Luckily now, it really depends on the community. Until now, I think that Go has been very much a project led by Google. Now they're actually opening much more feedback to the rest of the community and getting friction logs from them and trying to figure out how to improve the language. So we'll see what happens, but I hope there's no Go to. Yeah. Yeah.
So one very specific question and one general.
Okay.
So maybe I start with a general question.
Okay.
So you showed that, okay, there are some cool packages here and there on GitHub.
Yeah.
Is there actually a place where these kind of packages are listed and somehow reviewed, so we have more confidence that actually the stuff we just found is something that is of a good
So 3 places. Go.org, this one will return everything. So let's say you want to do things with matrices. You can search matrix. And it's going to tell you this one, which is actually probably the best package to use. They're grouped by number of imports and number of stars on GitHub. So that gives you an idea. Then the number of imports works, but also there's a little bit of an issue, and I think that it might have been fixed because the number is much lower now. But it included all of the forks. So that was a little bit misleading, but it also kind of gives you a little bit the idea of how often people use these packages. So GoDoc is a pretty good place to go. The other one is Awesome Go. It's a current list of Awesome Go packages. These used to be really useful. It grew a little bit too much. So you're going to probably be able to find a bunch of different things for, command line and bot building and whatever. But the problem is that at this point, basically everything that has been proposed, it has been accepted, which means that this list is a little bit too big, and not everything that is here is as good as they say. And then there's also the Go and Wiki here on GitHub that has working with Go. Yeah, it has a lot of different links, not only to packages. I know there's some place that has a bunch of different packages, but this is probably a better place to start. This is actually well maintained, and it's maintained by the Go community and trying to figure out what are the things that you should be learning, what packages you should be using, etc. So 3 places.
Thank you very much.
Sorry, can I interject in
Yeah.
the topic? Could you recommend some nice user interface cross-platform library?
Yes, so I got that question before too. The way I would do it personally is do not try to use Go to do like desktop applications, at least the front end. I would use Electron. So you're going to do a web UI, or Electron, or anything else that has a web UI, right? There's other options that might be faster, actually, than Electron. But you're going to have a web UI with HTML, JavaScript, and CSS. And then it's going to communicate through REST, probably, with the backend. And both can be running in the same place, right? So that's how I do it. For things that are not as much, for things that are not as UI standard things like buttons and menus and stuff like that, but you're more free to use whatever you want to do. SDL2 also runs with Go, and I have a package, github.com/campoy/flappygopher. And if you run it, it works. So this is all built with Go. So you can do, and I'm pretty bad. But yeah, you can also do that for games and stuff like that. But that's pretty much it. Go is more for backend stuff than frontend. So yeah, there's also a thing called Gopher.js that allows you to use Go on the browser. I would not use it, but if you feel like having some fun, it's definitely something worth trying. There was a second question.
So, if I remember correctly, if you have Go routines and then you're trying to call into C, they turn into P threads?
Yes. So, yeah.
Is there some thought about how to efficiently interface C?
So, yeah, okay, so there's a couple things in here. The first one is when you, let me see, there was a point where, yes. So when you're using Go routines and C threads, it mixes really mysteriously. So you need to be really careful. And there's libraries like SDL2 that say this thing needs to be called always from this thread. And if you call it from any other thread, the whole thing will crash. So Go has things like runtime lock OS thread, which means that this Go routine will always run in the same thread. And then C is happy. So there's fixes like this. Yeah, you need to do things like this in order to be able to say, okay, this Go routine is going to be working with this thread all the time, and then C will be happy because it will map it all the time to the same thing. In order to use C from Go, and actually, I thought I had that slide. Let me see. No, I did not. Okay, so I forgot to answer that question, but there was a question about how to call, how does the interaction between Go and other languages work? So, really? I'm pretty sure I had it. Disappeared. Okay, so there's a couple things. There's, if you want to use C from Go, there's CGo. And CGo works quite well. It is hard to use because the Go memory layout and the C memory layout are completely different. Go is garbage collected, C is not. So there's a lot of things that can go wrong. And but actually, the way it's done now, if it works at the beginning, probably you're fine. Because actually, the CGo will check for a bunch of different things, like the fact that you are not sharing pointers and keeping references where you're not supposed to, and things like this. So it became a little bit easier to use, but still kind of complicated. But if you want to call C from Go, CGo is the best way to do it. TensorFlow uses that, SDL2 uses that. There's a bunch of different things that use it. I also have a just for fun video on that, on how to use Festival Light that generates some voice. So it's a C thing, and I generate the little Go shim that allows you to call that library written in C from Go. That works pretty well. As soon as C starts using threads, and then Go starts using Go routines, that's when it becomes quite complicated. If you want to call C++, there's Swift. Swift? Yeah, it's actually called Swift. It's not the language, but actually a library called Swift. And that allows you, that's what Google uses to call C++ from Go. To call Go from C or C++, you can actually build Go libraries into C archive mode. That's what we call it. So it generates code that it's actually a DLL library that you can then open with C. So there's a build mode that allows you to make Go code that is compatible with C, which means that you can call Go from Python. It's actually relatively easy to do. That works pretty well. If you want to call Python from Go, or Java from Go, or any other thing that it requires either interpreter or a virtual machine, I would just say don't. Like, use 2 different servers and REST APIs. It's much easier, because otherwise it's going to get in a world of pain. Like, starting the JVM from Go, that's a bad thing. Yeah. Yep.
So, about all the packaging, so how do you know if, for instance, there's a security vulnerability in a package that you import? If a program's been built with basically this security vulnerability, and how do you make sure you basically easily update this? And how do modules come in, like Go modules?
So the question is, how do you make sure that your program doesn't use like versions of a library that might have security vulnerabilities? The answer is, you do not really know that right now. Go modules should be able to help fix that, because then the versions will be public and everybody will agree on the same. We will not have an NPM, but we'll be closer to having something similar to that, where you can have a list of the things that you should not be using. GitHub does it already. Github Supports actually will identify the versions of libraries that you're using, and we'll let you know on top. We'll say, hey, you're using this version of this library that has been marked as wrong. So for now, GitHub does it. Eventually, we'll get better to doing that. For now, yeah, no, there's not much to do that. Yeah. Yeah.
What's actually the status of the modules? Because I understand it's been partially released in 1.11, but you keep saying it's not official yet.
It's not official because it's an experiment, and it's still not set. So the way experiments with Go work is first, we integrate them behind an environment variable that is set to off by default. So that's where we are right now with modules. The next step is we set that variable by default to true, but you can still set it to off if you want to. And then we see whether more people complain. And then after a while, we just remove that environment variable, and the behavior starts being there all the time. So with vendoring, that's how we did it. With internal packages, that's how we did it. There's a lot of different things that we've been adding to the Go tooling, and that's how we did. Modules, we are the first step of those 3. So that's why things could change. I do not think they will change much, but they could still. So yeah, that's why I say it's not official, and I avoid teaching people about it until, that's the way to do things. Yeah.
So all the backward compatibility is also depending on that.
So the backwards compatibility of Go does not include its tooling. It includes only the language and the libraries in the standard library. So it does not include the tooling. So if the tooling breaks, if Go build, for instance, Go build might change its semantics, and now you say Go build of a package doesn't work anymore. You need to Go build of a path. Sure, that would not break the backwards compatibility. Yeah, I don't think it's something they would do, but they could. Is there a way to do more low-level profiling? What do you mean by more low-level?
Hardware counters and so on.
Hardware counters, I have no idea, to be honest. I've never tried. I would assume that if the hardware supports it with Go, you could somehow do it, because the good thing with Go is you can drop to assembly if you need to, quite easily. It's actually very well integrated. So for instance, if you look at gonam.org, actually github.com/gonam. Floats. No. There's one thing that does it. Oh, BLAS. So yeah, if you go BLAS here, probably you're gonna start seeing. No, I will not be able to find it, unfortunately. CBLAS? Is this the thing? No, I will not find it. But somewhere here, you'll be able to find that actually that is literally just a function name that says Go, and then right below assembly. So you can do that and create libraries that use your whatever hardware, specific hardware you're using. Then you should make sure that you protect it with conditional compilation things to say this only compiles when you're using this platform. But yeah, all of those things you can. I don't think there's a thing that exists, or at least I do not know about it. So go dark.org, maybe you find it. Yeah. Yeah.
How does the CPU-specific optimization work? So if you compile it on a certain class of CPU, how does it ensure that it will use whatever is available? Another interclass CPU might have some other independence.
CPU, or what are you saying? CPUs, yeah. So there's a couple things. One is the fact that when you're compiling it, it actually knows what is the platform you're running it on. So when you do go env, these are the environment variables that this takes into account. And there's things like Go OS, Darwin, Go architecture, which is AMD64. And those things can have specific things, specific formats for some platforms that say, hey, actually support this assembly instruction. So then the binary will actually use it. We support a lot of different ones, and it's automated. So normally it's pretty complete. The other thing is the number of CPUs. There's actually a library for that. Not a library. Go max procs. So you can set this to 1, for instance, and run your own program, and now you're saying you can only use 1 CPU. So you can set this up. By default, is the number of CPUs. So yeah.
There's a number of concurrent Go routines? Or?
No, this is the number of threads that you can stack. So in a single thread, you can have millions of Go routines, though. So this is the number of threads that, actually not even the number of threads, is the number of CPUs that you're allowed to use, and sometimes 2 threads will be spawned if you're doing things that block 1 thread to make sure that another one can still run.
Yeah, but this is ones that are going to be active at a given moment.
What do you mean?
The number of CPUs that you are allowed.
This is the number of CPUs that I can use total. The runtime decides how many you actually use. You're saying basically a cap on how many you're allowed to use. So for instance, in my machine, I actually don't know how many I have, but actually when you do go, go bench, these 4 actually is the number of CPUs that it's using. So if you do go max proc equals 1, it went away because now it's using only 1. You can say, so you can actually do even your benchmarks. You can decide how many CPUs you can use to try to see how much it changes. So yeah, that variable is what sets it up. The other variable that is interesting is go GC. Go GC is you can manage the garbage collector. It's just a float, so you can go from, actually it's a float, so you can go, basically it's 1 is use the normal thing, but you can double it or half it or whatever, or you can set it to off, and then there's no garbage collection, which means that Go will work much faster until you're out of memory, and then it will crash. Sometimes that's what you want to do. Sometimes very fast programs will actually be much faster with that because there's a lot of things that it doesn't need to care about, so it will be much faster if it finishes. Yeah. Maybe one last question? Nope. Okay, so the important thing here is if you have more questions, make sure that you send them to me. I'm always happy to answer questions later on. So that's on Twitter. That is my official email. The other one was the personal, but I didn't think about it and I just put it there. So campoy@golan.org, you can ask all the questions. And also share all of these slides with Maria, and I'm sure she'll share them with you. Thank you.